Imagine finishing dinner tonight and then not eating again until tomorrow evening. No snacks, no breakfast, no lunch, just water, maybe black coffee, and time passing. For most people, that idea sounds extreme. Some might even think it's dangerous. But what if I told you that somewhere around the 16-hour mark, your body quietly begins switching into a completely different biological mode, one that humans evolved to use for survival, repair, and energy efficiency. And when you extend that fasting window closer to 20 hours, something even more fascinating begins to happen inside your cells. Your metabolism changes gears, your hormones shift, your body starts burning stored energy instead of constantly demanding new food. And deep inside your cells, powerful repair systems begin turning on. Today we're going to walk through exactly what happens inside your body when you go 20 hours with zero food. Not just the surface level stuff you usually hear about fasting, but the deeper physiological changes that explain why fasting longer than 16 hours can feel so different. Some of these effects start slowly. Others switch on like flipping a light switch. And if you've ever wondered why some people swear by longer fasting windows while others struggle with them, by the end of this video, you'll understand what's actually happening beneath the surface. Let's start at the beginning. Most people today live in what scientists call a fed state. That means the body is almost always processing food. Breakfast, snacks, lunch, another snack, dinner, maybe dessert. Every time you eat, insulin rises. Your body stores some of that energy and uses the rest. There's nothing wrong with eating, of course. Food is essential. But the human body was never designed to be constantly fed every few hours. For most of human history, food availability wasn't predictable. Sometimes people ate large meals. Sometimes they went long stretches without food. And during those periods without food, the body learned to activate a completely different metabolic system. When you finish a meal, your body begins digesting carbohydrates, fats, and proteins. Blood sugar rises, insulin increases, and your cells absorb glucose for energy. For several hours, the body runs mostly on the fuel that just entered your bloodstream. But eventually, that supply begins to run low. Around 4 to 6 hours after eating, blood sugar starts gradually dropping. Insulin slowly falls as well. The body begins looking for stored energy. This is where your liver plays a critical role. Your liver stores glucose in the form of glycogen. Think of glycogen like a backup battery. When blood sugar drops, the liver releases this stored glucose back into the bloodstream to keep your brain and muscles supplied with energy. For the next several hours, your body runs mostly on this glycogen reserve, but glycogen storage isn't endless. Most people have roughly 12 to 24 hours of glycogen, depending on their diet, activity level, and metabolic health. And that means as fasting time increases, your body starts moving toward another energy system entirely. By the time you reach about 12 to 14 hours without food, insulin levels are now much lower than they were earlier in the day. Your body is beginning to tap into fat stores more actively. This is one of the reasons intermittent fasting became so popular. Lower insulin levels make it easier for the body to release stored fat. Fat cells contain triglycerides, which are essentially packed energy reserves. When insulin drops and the body needs fuel, hormones signal those fat cells to break down triglycerides into fatty acids. Those fatty acids are then released into the bloodstream and transported to tissues that can burn them for energy. At this stage, something interesting begins to happen in the liver. When fatty acids flood the liver during longer fasting periods, the liver begins converting some of them into molecules called ketones. Ketones are a special kind of fuel that your brain can use when glucose availability is reduced. Your brain normally runs mostly on glucose, but during fasting, it begins gradually adapting to ketones as an alternative energy source. This shift doesn't happen instantly, it builds over time. And somewhere between the 16 and 20-hour fasting window, ketone production starts becoming noticeably higher for many people. This is often the moment when people report something surprising. Instead of feeling tired or weak, they suddenly feel mentally clear. Focus improves, energy stabilizes, hunger sometimes fades. That mental clarity people describe isn't imaginary. It's linked to real biochemical changes happening in the brain. Ketones provide a very clean and efficient fuel source for neurons. In fact, many researchers believe the brain evolved to function extremely well during fasting periods, because historically, those were the times humans needed heightened focus to find food. Imagine our ancestors going an entire day without eating. If fasting made them sleepy and unfocused, survival would have been much harder. Instead, the brain adapts. It sharpens awareness. Attention improves, and the body shifts into a more alert state. But ketones are only part of the story. One of the most fascinating processes that begins activating during longer fasting windows is something called autophagy. Autophagy literally means self-eating, but don't let the name scare you. It's actually one of the body's most powerful cellular cleanup systems. Inside your cells, proteins and components are constantly being damaged by normal metabolic activity. Over time, those damaged components can accumulate. Autophagy works like a recycling program. Cells identify damaged proteins, broken mitochondria, and dysfunctional parts, then break them down and reuse the useful materials. This process is essential for cellular health. But here's the interesting part. Autophagy tends to increase when the body is not constantly processing food. When nutrients are abundant all the time, the body prioritizes growth and storage. But when nutrients temporarily decline during fasting, the body shifts toward repair and maintenance. Researchers studying fasting have observed that autophagy activity begins increasing after extended fasting periods. The 16 to 20-hour range appears to be one of the windows where this cellular recycling system becomes more active. This doesn't mean a single 20-hour fast magically cleans your entire body overnight, but repeated cycles of fasting and eating may help stimulate this natural repair system more regularly. Another major shift during longer fasting windows involves growth hormone. Growth hormone is often associated with muscle growth and athletic performance, but it also plays a role in fat metabolism and cellular repair. Interestingly, fasting can increase growth hormone levels significantly. Studies have shown that fasting for extended periods may lead to several-fold increases in growth hormone production. Why would the body do this? Because during fasting, the body wants to preserve lean tissue while still providing energy. Growth hormone helps mobilize fat for fuel while protecting muscle mass. This is one reason some people find that fasting, when combined with proper nutrition and strength training, doesn't necessarily lead to muscle loss the way many people assume. In fact, the body becomes surprisingly efficient at protecting muscle during short-term fasting periods. Another hormone that shifts during longer fasting windows is norepinephrine. Norepinephrine is involved in alertness, focus, and fat mobilization. When fasting extends past the early hours, norepinephrine levels rise slightly. This helps maintain metabolic rate and keeps energy levels stable. In other words, the body doesn't immediately slow down when you stop eating. Instead, it often becomes slightly more metabolically active in order to help you stay alert and capable of finding food. Now let's talk about hunger. Many people assume hunger simply increases continuously the longer you go without food. But biologically, hunger is more complicated than that. Hunger is strongly influenced by hormones like ghrelin. Ghrelin is often called the hunger hormone because it signals your brain that it's time to eat. But ghrelin doesn't rise steadily forever. Instead, it tends to spike at the times your body expects food. If you normally eat breakfast at 8 a.m., ghrelin may rise around that time. But if you skip that meal regularly, those spikes often begin shifting. Interestingly, many people who experiment with longer fasting windows report that hunger peaks around the usual mealtime, then fades after 20 to 30 minutes. By the time someone reaches 18 or 20 hours of fasting, hunger waves often come and go rather than steadily increasing. This is one reason fasting sometimes becomes easier with practice. The body learns the new rhythm. Meanwhile, insulin sensitivity can also improve during fasting cycles. When insulin levels stay elevated all day from constant eating, cells sometimes become less responsive to insulin signals. Fasting periods allow insulin levels to fall, which may help restore sensitivity over time. Improved insulin sensitivity means the body can manage blood sugar more efficiently when food is eventually consumed. But there's another effect of longer fasting windows that many people don't expect. Digestive rest. Your digestive system works incredibly hard throughout the day, breaking down food, absorbing nutrients, and managing gut activity. During fasting periods, digestion slows dramatically. This gives the gut time to reset certain processes. Some researchers believe fasting may also influence the gut microbiome, although this area of research is still developing. As the fasting window approaches 20 hours, several of these systems are now working together. Insulin is low, fat burning is elevated, ketones are rising, growth hormone is increased, cellular repair pathways are more active, and the brain is increasingly comfortable using ketones as fuel. When someone finally breaks the fast after this window, the body often becomes extremely responsive to nutrients. Protein is used efficiently. Glucose is directed into muscles and the liver, and hunger hormones reset again as digestion resumes. Of course, longer fasting windows aren't necessary for everyone. Some people feel great with 12-hour eating windows. Others prefer 16-hour fasts, and some occasionally extend fasting to 20 hours or longer. What matters most is how the body responds. Hydration, nutrient quality, sleep, and stress levels all influence how fasting feels and how effective it becomes. And while fasting can activate powerful biological systems, it's not magic. Nutrition during eating periods still matters enormously. The body still needs protein for muscle repair. It still needs healthy fats for hormones and cell membranes. It still needs vitamins, minerals, and micronutrients for thousands of biochemical reactions. Fasting is simply a tool that changes when those nutrients are delivered. For some people, the 20-hour fasting window feels like a powerful metabolic reset. For others, it may feel too aggressive for daily life. But understanding what's happening beneath the surface helps explain why fasting longer than 16 hours often feels like crossing into a completely different metabolic state. Your body isn't starving. It's switching systems. It's accessing stored energy. It's activating repair pathways. And it's tapping into survival mechanisms that humans have carried for thousands of years. The modern world gave us constant food access, but our biology still remembers how to function without it for a while. And when that fasting window stretches toward 20 hours, those ancient metabolic pathways quietly wake up again, working behind the scenes to keep the body fueled, focused, and surprisingly resilient. When the body moves deeper into a fast and passes the 16-hour mark, something subtle but powerful begins unfolding inside the cells. At first glance, fasting might appear to be a period where the body simply runs out of food and begins slowing down. But the reality is almost the opposite. Instead of shutting down, the body activates a collection of protective biological responses that are designed to help it adapt to temporary stress. These responses are not harmful stress in the way people often imagine. They are controlled, beneficial stress signals that push cells to become stronger, more efficient, and more resilient. Scientists sometimes refer to this process as a cellular stress response, and it is one of the most fascinating aspects of fasting that most people never hear about. Inside every cell of your body, there are tiny systems constantly monitoring the environment. These systems track things like nutrient availability, energy levels, oxygen levels, and damage inside the cell. When food is plentiful and nutrients are constantly arriving, cells stay in growth mode. They focus on building, storing energy, and reproducing new cellular components. This is the fed state that most people live in throughout the day, when meals and snacks arrive every few hours. But when the body enters a longer fasting period and nutrients stop flowing into the bloodstream, these cellular sensors begin noticing the change. Glucose levels decline, insulin drops, amino acids from protein digestion are no longer arriving. Energy molecules begin shifting towards stored reserves. The cell senses this change and begins activating pathways that are designed to help it survive periods of scarcity. One of the key systems involved in this process is known as the AMPK pathway. AMPK acts like an internal fuel gauge inside cells. When energy is abundant, AMPK activity remains low because the cell has plenty of fuel. But when energy becomes limited, AMPK turns on. When it activates, it begins sending signals throughout the cell that say, in effect, we need to become more efficient with our energy use. When AMPK becomes active during a fast, it encourages the body to begin burning stored energy rather than relying on incoming food. Fatty acids begin to move out of fat tissue and into cells where they can be used for fuel. Mitochondria, the tiny energy generators inside your cells, start working harder to produce ATP, which is the main energy currency used by the body. At the same time, AMPK signals the body to slow down processes that require large amounts of energy but are not immediately necessary for survival. This shift in energy management becomes especially noticeable during longer fasting windows like a 20-hour fast. The body begins prioritizing efficiency, and cells become much more careful about how they spend energy. But efficiency is only one part of the story. The cellular stress response also triggers repair mechanisms that improve the long-term health of cells. One of the most important repair systems activated during fasting is the process of autophagy. Inside every cell, proteins and structures are constantly being damaged through normal metabolism. Mitochondria wear out, proteins fold incorrectly, and waste products accumulate. If these damaged parts are not removed, they can interfere with normal cellular function. Autophagy acts like a recycling center inside the cell. Damaged components are identified, broken down, and then reused to build new structures. During periods of constant feeding, autophagy tends to stay relatively quiet because the body is focused on growth. But when fasting extends beyond the early hours, the signal for repair becomes stronger. During a 20-hour fast, autophagy activity begins increasing in several tissues throughout the body. Cells begin clearing out dysfunctional mitochondria and broken proteins. This cleanup process can improve cellular efficiency and may help prevent the accumulation of damaged components that contribute to aging and metabolic dysfunction. Another important part of the cellular stress response involves mitochondria themselves. Mitochondria are responsible for generating energy, but they are also sensitive to stress. When nutrients are constantly available, mitochondria sometimes become less efficient because the demand for energy production remains predictable and steady. But during fasting, energy availability fluctuates, and mitochondria must adapt to these changes. As fasting continues, cells begin activating a process known as mitochondrial biogenesis. This process encourages the creation of new mitochondria and improves the quality of existing ones. Essentially, the cell upgrades its energy production system so it can handle energy demands more effectively. Better mitochondria mean better metabolic efficiency. When mitochondria function well, the body becomes better at converting stored fat into usable energy. This is one of the reasons many people experience stable energy levels during extended fasting periods, even though they are not consuming food. The cellular stress response also affects how the body handles oxidative stress. Oxidative stress occurs when unstable molecules known as free radicals accumulate inside cells. These molecules can damage proteins, DNA, and cellular membranes. Normally, the body has antioxidant systems that neutralize these molecules, but when oxidative stress becomes too high, cellular damage can accumulate. Interestingly, moderate stress from fasting can actually strengthen the body's antioxidant defenses. When fasting extends toward the 20-hour mark, certain protective genes begin turning on. These genes increase the production of antioxidant enzymes that help neutralize free radicals more effectively. This phenomenon is known as hormesis. Hormesis describes the process where a small amount of stress stimulates a protective response that ultimately makes the system stronger. Exercise works through a similar principle. When muscles experience controlled stress during exercise, they adapt by becoming stronger and more resilient. Fasting creates a similar type of stress at the cellular level. Instead of harming the body, this temporary stress activates protective systems that strengthen metabolism. Hormones also shift during this period in ways that support the cellular stress response. One of the most interesting hormonal changes involves growth hormone. During extended fasting periods, growth hormone levels can increase dramatically. Growth hormone helps preserve lean muscle tissue while encouraging the body to use stored fat for fuel. This hormonal environment supports the metabolic shift that occurs during a 20-hour fast. Instead of breaking down muscle tissue for energy, the body becomes more focused on mobilizing fat reserves. This helps protect muscle mass while allowing the body to maintain energy production. Another hormone involved in this adaptation is norepinephrine. Norepinephrine increases slightly during fasting and plays a role in stimulating fat breakdown. It also increases alertness and focus. This explains why some people report feeling mentally sharp and energized during longer fasting windows. The brain itself also adapts to fasting by becoming more comfortable using ketones as fuel. Ketones are produced in the liver when fatty acids are broken down for energy. During extended fasting, ketone production rises, and the brain begins using these molecules as an alternative energy source. Ketones have several interesting effects on brain cells. They appear to support mitochondrial efficiency in neurons and may help protect brain cells from oxidative stress. Some researchers believe ketones also influence signaling pathways that promote brain resilience and long-term neurological health. During a 20-hour fast, ketone levels may not be as high as during multi-day fasting, but they are often elevated enough to begin supporting this metabolic transition. As the brain adapts to ketones, many people experience a sense of steady mental energy that differs from the ups and downs associated with frequent carbohydrate consumption. Another fascinating aspect of the cellular stress response involves protein management within the cell. Proteins must fold into precise shapes to function correctly. When proteins become damaged or misfolded, they can interfere with normal cellular processes. During fasting, cells activate systems known as heat shock proteins. These proteins help repair misfolded proteins and maintain protein quality within the cell. Heat shock proteins act like molecular chaperones, guiding damaged proteins back into proper form or directing them toward recycling pathways if they cannot be repaired. This protein quality control system becomes more active when cells experience moderate stress. Fasting appears to be one of the triggers that can stimulate this protective mechanism. Inflammation is another area influenced by the cellular stress response during fasting. Chronic low-grade inflammation is associated with many metabolic disorders, including insulin resistance and obesity. When the body is constantly processing food, especially high sugar or highly processed meals, inflammatory pathways may remain activated. Fasting provides a temporary break from constant digestion and nutrient signaling. During longer fasting windows, certain inflammatory signals begin to decrease. The immune system shifts toward a more balanced state, and inflammatory pathways may become less active. The metabolic improvements associated with fasting may partly come from this reduction in chronic inflammation. When inflammatory stress decreases, cells often become more responsive to insulin and more efficient at managing energy. Another key aspect of the cellular stress response during a 20-hour fast involves nutrient sensing pathways. One of the most important of these pathways is known as mTOR. The mTOR pathway controls cell growth and protein synthesis. When nutrients are abundant, mTOR becomes active and encourages cells to grow and build new proteins. But when fasting extends beyond the early hours, mTOR activity decreases. This slowdown allows the cell to shift its focus from growth toward repair and maintenance. Lower mTOR activity is also associated with increased autophagy and improved metabolic balance. Balancing mTOR activity appears to be important for long-term metabolic health. Constant activation of growth pathways may contribute to metabolic dysfunction, while periodic reductions during fasting allow the body to restore balance. Fat tissue itself also responds to the cellular stress signals triggered during fasting. As insulin levels fall and fat breakdown increases, adipose tissue begins releasing fatty acids into circulation. These fatty acids become a primary energy source for many tissues, including muscles and the liver. The process of mobilizing fat during fasting helps train the body to access stored energy more efficiently. Many people who eat frequently throughout the day rarely activate this system because their bodies rely mostly on incoming food for energy. Fasting teaches the body to switch more easily between different fuel sources. This flexibility in fuel usage is known as metabolic flexibility. Metabolic flexibility allows the body to transition smoothly between burning carbohydrates and burning fat depending on availability. flexibility. Individuals with good metabolic flexibility tend to experience more stable energy levels and better metabolic health. During a 20-hour fast, the body practices this fuel-switching ability in real time. As glucose availability decreases, fat metabolism increases, and the body becomes more comfortable using stored energy reserves. Another interesting aspect of the cellular stress response involves the immune system. Certain immune cells appear to respond to fasting signals by becoming more efficient at removing damaged cells and pathogens. Some studies suggest fasting may influence immune cell regeneration and repair, although this area of research is still developing. What makes the cellular stress response so fascinating is that it represents an ancient survival mechanism. Human physiology evolved in environments where food availability was unpredictable. Periods of abundance were often followed by periods of scarcity. The body adapted by developing systems that could handle both conditions effectively. During feeding periods, the body focuses on growth, storage, and reproduction. During fasting periods, it shifts toward efficiency, repair, and resilience. These two states work together to maintain metabolic balance. In modern life, constant access to food means many people remain in the fed state almost all the time. The fasting state rarely occurs long enough to activate the deeper repair systems built into human biology. Extending fasting periods occasionally allows the body to access those ancient metabolic pathways again. As the fast approaches the 20-hour mark, many of these systems are already active. Cells are using energy more efficiently, damaged components are being recycled, mitochondrial function is improving, and metabolic pathways are shifting toward fat utilization. These processes do not happen instantly, and they vary between individuals depending on diet, activity levels, metabolic health, and genetics. But the underlying biology remains remarkably consistent. The body recognizes the temporary absence of food as a signal to strengthen itself. This is why the term cellular stress response can be misleading. Although the word stress often carries negative connotations, this type of stress is actually part of the body's adaptive design. Controlled challenges stimulate protective systems that help maintain long-term health and metabolic resilience. During a 20-hour fast, the body is not simply waiting for the next meal. It is actively adjusting, repairing, and optimizing internal systems in preparation for the next period of nutrient availability. Cells continue recycling damaged components through autophagy. Mitochondria keep producing energy from fatty acids and ketones. Antioxidant systems remain active, neutralizing free radicals generated during metabolism. Hormones maintain balance between energy usage and tissue preservation. All of these processes combine to create a metabolic environment where the body becomes more efficient, more adaptable, and better prepared to handle both scarcity and abundance.